So what did we do till yesterday? We have completed till forward propagation, right? How many of you have completed till forward propagation? How many of you have completed till forward propagation? Okay. So not a problem. We'll quickly recap on how did we come till forward propagation for 5 minutes. So those who have missed the class can follow up with that. And then after we are done with forward propagation, let's see the next step, which is what? Error calculation. Very good. After error calculation, what do we do? Backward propagation. So today in this session, we would complete loss calculation and how do we do backward propagation. Okay. For 15 minutes when I'm discussing theory, I request all of you to please stop working on your laptops, because when you miss this session, you'll not be able to code properly and you'll be getting 0 by 100 score. Please listen to the session for 15 minutes. We'll on the exercise and you can please carry on with that. Okay. Yeah, so we'll have quick recap on what did we come till now. After that, we'll discuss on how do you calculate error, and then we'll see how backward propagation is done. Okay, calculating gradients. Okay, so these are the 5 important steps that we usually implement when we want to design a neural network. Okay, so what do we do in the beginning? We go for data loading or data pre-processing. So we first load the data set, do some data pre-processing. Okay. So what was the pre-processing step that we have used for this particular exercise? Standardization. Okay. So everybody must be able to answer. In the last session when Neil sir was asking, nobody answered this question. Why do we do standardization? To give equal importance to what? All the features. Because all the features may have different range of values. Okay, so when we go for training the model should not interpret the importance of different features based on high and low values. For that reason, we go for standardization. That was pre-processing which we have done. Okay, so after pre-processing, what do? We go with what? Forward propagation. Okay, what is forward propagation? Multiplying weights with the inputs and adding bias term to it. Okay, after we do forward propagation, we go with loss function. Okay, in forward propagation itself, after we multiply weights with input and add bias, we also apply that to activation function such that we will know which neurons are activated and the importance of each neuron. Okay, so after we do forward propagation, we go with what? Error calculation. So if the error is more or if the loss is more, we go for backward propagation. We apply gradient descent such that the weights would be adjusted. Weights and biases would be adjusted, which will actually reduce the loss. When the loss is reduced, the accuracy of your model would be increased. The low the loss is, the high the accuracy of the model would be. Okay. So after we do backward propagation, we go for training the model. That is, we put a train. See, we are all defining the functions here. So we define a function for forward propagation, we define functions for activation function, we define a function for backward propagation, we define function for loss calculation. In the training, we put these things in order. When I say order, we first do forward propagation and then call loss function and then call backward propagation. This is how we train the model. So when I train the model, I add some epochs. Epochs is nothing but how many times do we have to run the model until the desired accuracy is reached. Okay. So in the training loop, we take care of all these things. And then we go for testing where we try to predict our model's performance. Okay. So till last session, we have completed till what? Forward propagation. Okay. Yeah. So this was the structure. Okay. Yeah. So when I talk about loading and pre-processing, we have done standardization. And then when it comes to activation function, which activation function did we use? ReLU. Okay. Now, so many of you had one doubt yesterday about identity function. Let me clear you that. Okay. Now listen. Basically, when I talk about a simple neural network, okay, we have one input layer, we have one hidden layer, and we have one output layer. Okay. So what is this W1? The weights which we are adding from input to hidden size. What is W2? The weights which are adding from hidden to output layer. Okay. So there are two connections. Input to hidden layer is one connection where we are adding W1 and B1. Hidden to output where we are adding weights W2 and B2. This is how we progress, right? Now when I talk about activation functions, okay, we use one activation function at the output of the hidden layer and we use one activation function for the output layer. So we use two activation functions in general. Okay. Now, when I talk about this regression model, The activation function that we are using for the hidden layer is what? ReLU. Why are we using ReLU? Because I want my output or target variable has continuous values. So I use what? ReLU, which will actually, what is the formula for ReLU? Max of 0, x. Okay. It will return x if the value is not 0, otherwise the value would be what? 0. Okay. Now, when I talk about activation function for the output layer in regression, I don't want to take sigmoid. Why do we take sigmoid? For binary classification where we have only 2 possibilities. But for regression, I have so many continuous values. So I cannot take sigmoid. Okay. When do we take softmax? For multi-class classification where I predict my class based on probability of the value. If I say I have car, bike and lorry. Okay. So depending on the shape of the object, I want to check whether it is car, lorry or bike. Okay. Now I'll have the probability of the features. So for which we go for which function? Softmax function. But when it comes to ReLU here, when it comes to regression model here, I want all my continuous values after ReLU to be displayed directly. So I can take Z2 as A2 directly. What is Z2 and what is A2? What is Z1? Z1 is, please understand, Z1 is W1 X1 plus B1. What is A1? Activation function which is applied on Z1. What is Z2? Weighted sum of A1 into W2 plus B1. Now here in this case for regression, when we are talking about regression, you can take Z2 as your output directly. Okay. But for, for proper neural network design, it is good to put into practice giving activation function for hidden layer and output layer as well. But for regression, I want to take my Z2 values directly. So I don't want to take Z2, but I want to take some function or some activation function kind of thing, such that I'll have hidden layer activation function and output layer activation function. So there's nothing changed. Even if you go for identity or without identity, it would be the same. Z2 would be the same. But just for following the hierarchy, I go for introducing one matrix which is called as identity matrix, which serves as activation function for the output layer. That's all. Is that clear? For when you go for classification model, you can take one activation function for the hidden, one activation function for the output layer. Are you all clear now? Yes or no? So always put into practice giving activation function for the hidden layers, activation function for the output layer. Here in this case of regression, my Z2 values from the first activation function should be taken directly. But instead of doing that, I am also taking A2 variable where that is nothing but the same thing from Z2 which is passed. Okay. Now, yeah. So after we define activation function, we have seen forward propagation. Okay. Now Z1, A1, Z2 and A2. So what is Z1? Weighted sum of input and first weights plus bias. A1 is nothing but activation function of Z1. Z2 is nothing but weighted sum of A1 and W2 plus B2. Now here A2 is nothing but what? Identity of Z2. You can skip that, but for proper network. Okay. Now this is what we have done. Okay. Yeah. You might skip the activation function that we have taken, identity matrix, but better you put into practice. So I have given you technically and practically. Technically it is not required, practically it is good to put into practice. Okay. Yeah. So what are we going to do today? We have to calculate loss function. So I have discussed about 3 loss functions. Okay, in the initial classes I have discussed about 3 loss functions. One is mean squared error, which we use for what? Regression. Okay. Second one is cross entropy. We have 2 types of cross entropy again. Binary cross entropy, categorical cross entropy. When and where do we use binary cross entropy? For binary classification, where your output variable is either yes or no, 0 or 1, true or false. Only 2 possibilities of the output variable. When do we use categorical cross entropy? When you have multiple classes. When you have multiple classes. That is when I talk about a feedback. Okay. So it's say she's good, she's average, she's excellent, she's extraordinary, she's outstanding. Okay. So I have different classes here. So when I have different classes of output, I go for what? Multi-class classification. In that case, we use categorical cross entropy. So the exercise we are working on is about regression. So which loss function do we use? Mean square error. What is this mean square error? Basically, loss is nothing but difference between actual value and predicted value. What is that? Difference between actual value and predicted value. Now listen to me very carefully. In the data set, we have divided the data set into X and Y, right? What is X? All the input features. X is what? All the input features. Okay. What is Y? The target variable. Y is nothing but the target variable. So Y is nothing but in Y I have my actual values. In A2, what is A2? The predicted output. So how do we calculate loss? A2 minus Y. What is A2? Predicted output. What is Y? The actual output. Okay. So the difference between actual and predicted is nothing but your error. Okay. But I don't have one sample. I have 100 samples in your data set. So I can't consider only one sample. That is one thing. And second thing, when I calculate this loss, sometimes the expected value may be above the actual value, or sometimes the expected value may be below the actual value. So that is the reason we go for squaring. That is the reason we go for squaring, because the negative value becomes positive when you square. So we have two things again. We have MSE and MAE. What is MAE? Mean absolute error. So when you take absolute also, the negative would be turned to positive. So you can either go for MSE or MAE, but most probably will prefer MSE. Okay, that is the reason mean squared error. What do you mean by mean? Average of squaring of all the samples. So what is the formula here? A2 minus Y whole square. What is A2? Predicted. What is Y? Actual. Why are we squaring? Because I want to convert my negative to positive. And then why am I doing summation? Sum of all the samples and then take the mean of it. So that is the reason. What is the formula for MSE? 1 by M summation of A2 minus Y whole square. Are you all clear with this? Yes or no? Why is that called as mean square error? Clear? Yeah. So this is the formula for that. Okay, don't go with the symbols. Here I have kept Y cap. Y cap is nothing but A2. Don't get confused. Okay. So 1 by M summation of I is equal to M. That is starting from first sample to the end sample. I want to do summation of predicted value minus actual value whole square. So this is how we calculate what? The loss function. Are you all clear with this? If yes, I'll proceed. Okay. Okay, now this is the entire structure for backward propagation. Okay, please observe the figure very carefully. Okay, so first I take my input X. What am I taking? Input X. Okay, now what am I doing with that input X? I add weights W1 and bias and calculate Z1. So what is Z1? X into W1 plus B1. I apply activation function for this this is called transfer function, as sir was discussing. Transfer function is nothing but X into W plus B. Okay. So in the neuron, first I calculate my transfer function and then I'll apply that to activation function, which is A1. Okay. After activation function, I go with what? Yeah. So X is multiplied with W1 plus B1. This is called as transfer function, which is nothing but Z1. After Z1, I'll apply that to activation function, which is A1. So this is how I complete my input to hidden. Okay. Now when I talk about hidden to output, what am I doing? I am adding W2 and B2 to what? A2. Not X again. Sorry, A1. Okay, I am adding W1 and B1 to what? A1. Okay. Now, after I calculate Z2, what do I do? For regression, you can go for Z2 directly, but as I have taken A2, which is identity of Z2, you can add that. Okay. So as you can see, X is nothing but input data. Y is nothing but true label or the actual output. Z1 is nothing but linear output of the hidden layer before activation. See, you must be able to tell in this way. That is the reason I have put up what is Z1 and all that. So how do you say what is Z1? Linear output of the hidden layer before activation function. What is A1? Activation output of the hidden layer. What is Z2? Linear output of the output layer before activation function, and A2 is nothing but the final output, which is predicted output. So A2 is predicted output, Y is the actual output, X is the input. Are you all clear with this? Yes or no? Now let's see how do we do backward propagation. Okay. Now backward propagation is all about calculating derivatives. Calculating what? Derivatives. So first there are 5 derivative calculations. Okay. How many derivative calculations? 5. Okay. First we calculate derivative of A2 with respect to a loss. Okay. So that is the predicted output. Okay. So that would be A2 minus Y. Okay. Next we calculate derivative of W2 and see backward propagation is from output to input. So first I'll get what? W2 and B2. So first I'll calculate loss of what? A2 and then derivative with respect to W2, B2 and then derivative with respect to A1 and then derivative with respect to what? W1 and B1. So I'll go in the reverse way. So we'll see those 5 steps. Are you all clear with this figure? Please understand what is X, what is Y, what is Z1, what is A1, what is Z2, what is A2 and what is the final output. Okay. Now, what do we do first? First we calculate derivative of Y, derivative of loss with respect to what? Y. Okay. Now that is nothing but, see when I apply derivative to my loss function, what is loss function here? 1 by m summation of A2 minus Y whole square. So when I apply derivative, I'll get 2 by m of A2 minus Y. That Y cap is A2. Okay. So 2 by m of A2 minus Y. So as 2 by m is a small scalar value, I'll simply discard that. Okay. So in practice, when implementing backward propagation, the factor 2 by m is sometimes omitted for simplicity. So the derivative of the final loss function would be taken as A2 minus Y. Okay. So this is the simplified expression. So what is the first thing? Derivative of loss with respect to output? A2 minus Y. This is first. I told you about 5 calculations, right? So the first calculation is the final output derivative calculation, which is what? A2 minus Y. Okay. Now these are the 5 steps that I was talking. First you have to calculate derivative of loss with respect to Z2 or A2 in our case. Okay. After that we have to calculate gradients for W2 and B2. Then calculate gradient for A1 and then we calculate gradients for the activation function Z1 and then we'll calculate the gradients for W1 and B1. These are the 5 steps that we do in backward propagation. I'll explain each of them in detail. Just note them down. Okay, what are the 5 derivative calculations in chain rule for backward propagation? First is what? Derivative of loss with respect to Z2 or A2. Okay, so if you don't take identity matrix, it will be Z2. If you have taken identity matrix, it would be A2, but both are one and the same. Okay, after derivative calculation for Z2, I go for what? Gradients calculation for what? W2 and B2. See, when I say gradient calculation, this is where my W2 and B2 values would be changed. Okay, why am I changing W2 and B2 values? Because I don't want my input to change. I want the weights assigned to the inputs to change such that I reduce my loss function. Are you all clear with that? See, there's no point in changing the input. If you change the input, obviously you may get good loss function. You may get reduced loss function. I don't want to do that. I want to take the same inputs but try to reduce the loss function by adjusting what? By adjusting my weights and biases. So that is where I calculate my gradients for W2 and B2. After that, what do we do in third step? We calculate the gradients for what? A1. What is A1? Activation function after the hidden layer. Okay. Now fourth one I calculate gradients for what? The activation function. Okay. And then, derivative of the activation function. And then finally I'll calculate the gradients for W1 and B1. In this way, we'll try to change W1, W2, B1, B2 such that they reduce my loss function to get the desired accuracy. Okay. Now we'll see how do we carry on with each step. Okay. Yeah. Ma'am, zoom in, no? Okay. See, if you understand these 5 steps, backpropagation is very easy. See, the complicated part of a neural network designing is backpropagation. Why? This is where my actual training starts. This is where my accuracy would be improved for the model, right? So listen to these 5 steps very carefully, please. Okay. So what do I do first? What do I do first? Calculate my derivative with respect to output, which is A2 minus Y, which I told you. Okay. Now, when I talk about computing gradients for W2 and B2, the gradient of the cost function with respect to what? Weights and biases. This is where W2 and B2 gets changed. Okay. So, somebody asked me yesterday, Mom, why are we taking bias as 0 initially? Initially, we take bias 0. I don't want anything to get disturbed. Now when I calculate the loss function and know that my loss function is very high, then I'll change my biases here by calculating the derivatives. Okay. So in this particular step, you have to compute how much weights from the hidden layer to the output layer should be adjusted. How do I adjust my W2 and B2 such that I can reduce my loss function? So that is the reason I calculate W2 with respect to what? Z2. Got it? Next, dB2. What is dB2? Same way I adjust my weights, I also adjust my bias term. Okay. Now after that, I'll compute my derivative for activation function. I compute the derivative for the hidden layer, which is Z1. Then finally, I'll calculate gradients for what? W1 and B1. So this is gradient descent. This is one algorithm which is called as gradient descent algorithm. Okay. Not just gradient descent, we have so many other optimization algorithms which we will use in the next preceding exercises. Okay. Yeah. You can see this. You can note these formulas because you are supposed to write the code for this block using this only. Okay. So what is dz2? A2 minus y. Okay. Now look at this. This is very important. Now when I say calculating gradients for W2 and B2, I write dW2 is equal to 1 by m A1 transpose dZ2. Why do I have to take transpose there? What is A1? Activation function of the hidden layer, right? What is dZ2? Linear output. Now here, the size of the number of neurons in the output layer may be different. The number of neurons in the output layer may be different and the hidden layer it may be different. For example, listen to this very carefully. Let's say A1 size would be number of samples comma neurons in the hidden layer. This is very important. Please listen. If suppose I have 100 samples, the size of A1 would be 100 comma the number of neurons in the hidden layer. If let's say I have taken 10 neurons in the hidden layer. So the size of A1 would be 100 comma 10. Now when I talk about Z2, I have only one output because it is regression. Okay. Samples are same. 100 comma 1. Now can I find the derivative with respect to this different size of matrix here? No. So that is the reason I apply transpose to A1. Now when I do transpose, I get what? 10 comma 100. Now I can easily perform dot product of 10 comma 100 and Z2 which is 100 comma 1. Is that clear? Yes or no? For ease matrix calculation, we do the transpose of what? A1 to match the size of what? A1 and Z2. Are you clear guys? Yes or no? So I do that W2 and then what is dB2? To calculate dB2, I'll go for 1 by m summation of all the values with respect to what? dZ2. Similarly, I'll calculate my gradient for A1. I'll calculate the derivative with respect to ReLU activation function and then I'll repeat the same with for W1 and B. Now look at W1. I go for X transpose. Why am I taking X transpose? Because for W1 my input is what? X. When I talk about W2, W2 is taking input from A1. So I take A transpose there. Please make a note of this. W2 is the input, for W2 the input is what? A1. But whereas for W1 the input is X. Hence I take X transpose into dZ1. So this is how I calculate my gradients for dZ2, dW2, dB2, dZ1, dW1. Are you all clear with this? So these are 5 steps for deriving the function for backward propagation. Okay. So I think we'll be doing this today. Okay. So you are supposed to do what? Calculate loss function, define a function for calculating loss function and define a function for backward propagation in how many steps? 5 steps. dZ2, dW2, dB2, A1, ReLU, and then DW1 and DB1. Any doubts in this? Any doubts in this? See, I have given you the formulae. I have explained you all these 5 steps. You should be able to do it properly. No 0 by 100 today. Okay? So, on the exercise, you can start working on it. Yeah. So, I have a small question for all of you. Okay? So, how many of you are finding it difficult to solve that? See, if you have any difficulty, please feel free to tell us. Okay? So, we are here to help you out. Now, see, the problem with you guys is you won't listen when we explain. You'll be busy on your systems. What I explain, the same question you get after you work. Please don't do that. Listen to us. Once we are done with this, you can please work on it. Okay? So, for those who are finding it difficult to code, I'll tell you how do you write it. Okay? I'll explain for forward propagation. Try using this methodology and try to do it for backward propagation. Is that clear, everybody? Yes? Yes, listen now. What do we do in forward propagation? What are we doing? What do we do in forward propagation? Okay, I'll switch on to this. Yeah. What do we do in forward propagation? All of you know the theory at least. How many of you are finding it difficult to understand theory as well? Okay. Theory also? Okay. So, what do we do in forward propagation? Multiply input with weights plus add bias term to it. So, that we call it as Z1. So, my input is X, weight is W1, B1. So, that I am calling it as what? Z1. So, Z1 is what? X plus X into W1 plus B1. Okay. Now, what is A1? After I take this transfer function Z1, I apply my activation function to that, which is called as what? A1. So, what is A1? ReLU of Z1. Next, what is Z2? Z2 is hidden to output. So, hidden is A2. Okay. So, A2 into W2 plus B2. So, this is the theoretical part of how do we do forward propagation. Now, let's switch to the code. Press that button. Yeah. So, look at this. I'll tell you how did I write the code for doing that forward propagation. So, I'll define a function called forward underscore propagation and I'll pass some parameters to it. So, what are the parameters that I am passing? X, because that is the input. Now, I also want to add W1, B1, W2 and B2. Did you all understand this? So, you have to define a function and pass the parameters which are required for defining that function. Okay. Now, once I am done with that, now I'll calculate Z1. So, what was the formula for Z1? X into W1 plus B1. So, I am finding the product of what? X into W1. So, what is the function in NumPy that we use? NP dot of what? X comma W1 plus B1. Okay. Now, what is A1? ReLU, already I have defined ReLU of Z1. So, what is Z2? NP dot of A1 in A1 comma W2 plus B2. So, after that I have applied, see, this is, I put ReLU, but it is identity of that thing, or if you are not taking anything, it is like that. Are you all clear with this? Yes or no? Now, how do you do for backward propagation? Define backward underscore propagation, pass the parameters that are required for backward propagation. Next, we'll declare what? dz2 and then dw2, db2, da1, dw1, db1. You have seen the formulas, right? So, with respect to that, we'll open up the formulas in the projector. Okay? You can see that formulas and write your function. Okay? So, if you still have doubts, we'll come and help you out because I can't waste time because most of you have understood that as well. Okay? So, we'll put up the formulas, we'll open the exercise, look at the formula and try to code. Is that clear now? Okay, if you have any doubts, you can please raise your hands. All of us are here, we'll be coming to you and help you out. Okay? Chalo, carry on. Yeah, this is loss function. Okay? So, that y cap is nothing but A2 as per our code. Okay? So, please use the same terminology. Don't put y cap. Even if I am saying this, many of you will do that, I know it for sure. You call me that you are getting error. I repeat, don't take y cap there, it is A2. Okay? So, So first calculate loss function MSE. Find a function called compute underscore cost. And what are the variables that I have to pass to this function? A2 and Y. What is A2? The predicted output. What is Y? The actual original Y outputs, okay, in the data set. So first, when I calculate my formula for MSE, I need M, right? So M is nothing but the total number of samples that I have in the data set. So I take Y dot shape of 0. So you can take mean directly. You can use your own formulas. That's not a problem, okay? So we have just taken M is equal to Y dot shape of 0. So wherein M will have the total number of samples that are there in Y. And then I say cost is equal. So I say cost is equal to 1 by M into, so what do I do here? NP dot sum of A2 minus Y. Okay, A2 minus Y whole square. And then I say return the function. Okay. So here we use NP dot, I am using NP dot squeeze of the cost value. So why do we use squeeze in NumPy? To return the scalar values. See, here in our data set we have only scalar values, that is okay. But sometimes when you work, see, it is not mandated to use here, but I want to introduce you to this. Okay. So in the data set, if you have any other values like, matrix 1, 2D array and all that, to get it into scalar values, we use this function called squeeze. For here, the data set that I have given you guys, insurance is all scalar values, so that does not matter. But I want you to know what is squeeze function used for. Okay. Because when you work on other data sets in the future, so all the values may not be scalar there in the data set. So you have to use squeeze function there.
No, how do you calculate MSE?
Are you all clear with this? Because see, the procedure for all the exercises or all the things would be same except the change of loss function, except the change of your optimizers. Same steps would be there. So please make sure that you're doing this exercise with clear understanding. If you understand this exercise, you can do all other exercises on machine learning and deep learning. Okay. If you don't understand this, you'll not be able to do. That is the reason we are going very slow. Okay. Block we are doing it separately. Okay. Now try to work on backward propagation for some time. We'll try to explain you, but we want you to work on it for some time by yourself. Formulae? Okay, we'll switch on to that.
Okay. We'll wait for at least 20 so that I can execute it.
Where everybody are going wrong is, here when we talk about M, it is X dot shape because we are processing the inputs here. When I talk about loss calculation, it is Y dot shape because for loss I need my output. So M stands for number of samples in the output one column. But here I have to take what? Samples of X with all rows. So axis is equal to 0. Why do we take axis equal to 0 and axis is equal to 1? When I want to access one column values, I go for axis is equal to 1. Right? So here axis should be kept to 0 because I want to access all the row values of all X. So I find the shape of X, which would be M, and I have to access all the values of X. That is all features, all values of X. So I put axis is equal to 0. So these are the two things where all of you are going wrong. Yes. Okay. So here M would be shape of X because I want to access all the inputs. With respect to inputs, I want to change my gradients W1, W2, B1, B2. So X is nothing but, M is nothing but shape of X, and you have to put axis is equal to 0 because I want to access all the row values of X. Okay. So if you incorporate this, I think you can do this part of code. Now look at that. Yes. So I have defined a function called backward propagation. So what are the parameters that I am passing here? X obviously because I want from X to Y. So I take X, I take Y, and I am taking what? Z1, A1, A2 and W2. Okay. Now look at this. So here M stands, all of you please listen to me. I want to take all the input features and all the values in the input features. Let's say I have 4 input values, age, weight and all that. Okay, so m is nothing but the size of the inputs. Okay, so I take m is equal to what? X dot shape. Okay, and then how am I calculating dz2? It is simply a2 minus y. This is okay with everybody. I know, I hope all of you are okay with this. Okay, now look at this. How am I calculating dw2? 1 by m into dot product of what? A1 dot t comma dz2, because dz2 I have already calculated in the above step. Okay, so after this I have to calculate db2. Okay, now look at this db2. All of you see this db2. So what is the formula for db2? 1 by m into summation of what? dz2. Okay, now look at this. Why am I taking axis 0 here? Because I want to access all the values in the rows of x. I want to process all my x values and then update my bias term. So that is the reason I am taking axis is equal to 0. And there is another parameter that I am passing, which is keep dimensions is equal to true. That is only for preserving your output. See, when you are basically doing mathematical operations in NumPy, when you use sum, mean, to preserve the dimensions of the output, we take dimensions is equal to true. Okay. Now we want you to do it for dw1, db1, dz1 and all that. Okay. So it is up to you now. Remaining things at least we want you to try. Okay. Half of the code is here. The remaining at least you should try. See, you should understand the terminology. What is Z1, what is A1, what is Z2, what is A2, what is W2, what is B2 and all. Product of what? Dot product of dz2 and w2 transpose.
60, sir. Okay, those who have done, please submit. And don't worry, we'll just check why. If there is a code error, we'll try to see why there is a code error. If there is a logical error, sorry, we can't do anything. Okay? Please submit, because we want to stop it and we want to discuss the solution now. We're going to discuss the solution. We are going to stop. Just submit. Don't worry about evaluation. Just submit. That's it. So we're going to stop. Yeah, Madam, please stop it. Yeah, ASHA, okay, yes, explain. Yeah, please look at the code now. We have stopped the summations. Understand that there will be a follow-up exercise coming week on this.
Okay. Now, look at that. So those 5 steps that I was talking about, that was dz2, dw2, db2, what next? da1 and then dz1, dw1, db1. Okay. Now when I talk about db, what is db? Derivative of loss with respect to bias terms. So in this case only we have to take axis is equal to 0 and dimensions, because I want to add the bias term based on all the values of the input x, for which I put x, axis is equal to 0. Okay. So don't put axis is equal to 0 for weights. Okay. How do we calculate weights? dw2 and dw1. How do we calculate weights? dw2 is nothing but dot product of A2 and dz2. What is dz1, dw1? Dot product of x with respect to dz1. See, you understand the structure of the network. You understand the parameters, what is x1, w1, x2, w2 and all that. So then it will be easy. Okay. So we take axis only for bias terms, weights w2 with respect to A2, w1 with respect to x. This is what you have to understand and remember. So your coding would be easy. Okay. Now where am I taking ReLU derivative? See, don't take ReLU here. You have to take ReLU derivative here. See, when we were defining ReLU function, we have also defined ReLU derivative. So I have told you there, ReLU derivative is used for backward propagation. Only ReLU is used for forward propagation. Please understand this. Okay. All of you please listen. We have defined ReLU and ReLU derivative, right? ReLU we use in forward propagation. ReLU derivative we use in backward propagation. Okay. So these are the mistakes that you have done. Few of them have used only ReLU. You are supposed to use ReLU derivative. Axis 0, dimensions are used only for maintaining proper dimensions of the output. When you are using NumPy, when you work on sum and mean, to retain the dimensions, we use keep dimensions is equal to true. Okay. So axis is equal to 0 and dimensions true only for bias terms, not for weights. So are you all clear with this now? Any doubts still? Any doubts? So will you be able to do backward propagation all by yourself for the next exercise? Yes or no? Huh. Okay. Chalo. See you in the next session.